Okay, so thank you for the opportunity to give this talk. I'm going to sort of flesh out a bit what I talked about in my short talk, and that's estimating quasimodes or eigenfunctions for semiclassical pseudo-differential operators. So let's have a look at the simplest form. We're going to consider an eigenfunction of a Laplacian. So we're working in the background of a Riemannian manifold M that doesn't have a boundary, and we'll have a sequence of eigenfunctions uj with eigenvalue lambda j squared. What we'd like to know is how large can these uj be, where can they be large, and what do these concentrations look like. So down here I've got a couple of the possible concentrations. So you have a point-like concentration. It's really the simplest kind of concentration you can have, and that's characterized by a very high L infinity norm, but it's very big over a very small area. So this area is about lambda inverse, one oscillation. On the other hand, you could have something like this tubular concentration. In this case, we have a long direction, which is about order 1, and then oscillations mainly in that direction, and a concentration around, say, a geodesic. At the completely other end of the spectrum, you have something that is physically dispersed. It does not have any concentration. It may have a concentration in frequency, but it doesn't have a physical concentration. So the first set of estimates that fall under this grouping are SOGS eigenfunction estimates for taking the LP norm of U over the full manifold and comparing it to the L2 norm of U over the full manifold. So we would always assume that this L2 norm here can be normalized to 1. Now in this case, he got that there was polynomial growth in lambda j, and that the growth is given here. This picture we plot delta against 1 on p. So a couple of important things to note. The L infinity norm, it goes as lambda to the n minus 1 on 2. This was already known. It's part of Weil's counting function, goes back to sort of Hormander. So we already knew this. You already knew the L2 norm is obviously quite trivial. Now you could just link these by interpolation, but that wouldn't give you the sharp estimates. These are the sharp estimates, and they have a very specific form in that there's a kink. And this critical value of 2n plus 1 on n minus 1 gives us where the regime changes over. For high p, we get optimized estimates when we take a point. So L infinity is the highest here, and for very high p, you want a point to optimize your estimates. You come down to this critical point, and suddenly it changes into a tube to be the optimal estimate. So these two regimes give the two sides of the kink, and this point here is sharp in both regimes.
Is this tube like having a concentration along a line or a curve?
Yes, that's exactly what it is. Okay. In higher dimension, it'll be a little lambda to the minus a half concentration around.
It could be in higher dimensions. You could have it not just along a long, or well, you could have it along a tube, but you could have it along a hypersurface. How should I think of that in that case in high dimension?
Well, in high dimensions, the optimal example is actually a tube. It is the tube, and there's one long direction, and all of the other directions are the same kind of concentration. You can have other things happening, but the sharp example comes from that tube.
Oh, and there are examples of these, right?
Yeah. There are examples. So SOGS estimates are for spectral clusters, and you can always find sharp examples for spectral clusters. But in fact, for spherical harmonics in the higher dimensions, you can find exact eigenfunctions which optimize these estimates. And that's because of high multiplicity. So a spectral cluster includes a sum of width 1. If there's a very high multiplicity, one can open up a window that includes only one eigenspace. And so you can get the concentrations for actual eigenfunctions.
In fact, at the kink, where lambda has a power which is, so for people 6, the power of lambda is 1 over 12.
So it depends on what lambda you're using.
Okay, well, I'm using the square root of, so it's lambda 1 over 6 maybe in your language.
Yeah, it's lambda 1 over 6.
What I wanted to say is that even for a flat torus, not a flat torus, but an integrable torus, you can saturate this. This part is going to be saturated from the necessarily only for things like a sphere, but
Yeah, yeah.
I think there was
There are
The
other,
top one?
these ones,
The lower one.
Kink.
Yeah.
the kinks. The kink, this point is
Oh,
always,
the kink.
the king.
the kink is always the interesting point. And finding that's always the difficult part of any of these estimates. So another way we can look at this, and this is what Berkshire Arden Zvetkov did in 2007, is take cross sections. So we let Y be a k-dimensional submanifold, and we're going to try and measure the LP norm restricted to Y and get some kind of similar form of the estimate. And these are the estimates they obtained. So firstly, there's a difference when you're looking at hypersurfaces and lower dimensional submanifolds. Lower dimensional submanifolds are actually quite simple. You only have the point-like concentration as the sharp estimates, and there's no kink to discover. However, when you look at a hypersurface, you haven't lost too much spatial information by taking a hypersurface, and you do still have a kink-like behavior, only the kink has now moved. So you have to redetermine where the kink is. And the same as before, the sharp estimates for large P are the points, and for low P, it's the tubes. So we're very interested, particularly in hypersurfaces, because of this change of regime. So I've been working at this kind of problem, but in the semi-classical framework. So rather than looking at a Laplacian eigenfunction, we're looking at a semi-classical quasimode. So this is just an example of how you might go between a normal differential equation and a semi-classical operator. We just rearrange this typical Laplacian plus V. Here we obtain that U satisfies a differential equation that depends on some small parameter. So we define lambda inverse equal to H, and that's going to be the small parameter which we'll use to encode energy into our operator. And we use a very similar idea to the Fourier transform method for solving a PDE. That is, instead of going from multiplication on the Fourier side to differentiation, we go from multiplication on the Fourier side to a scaled differentiation. So you should always understand a frequency as I write it xi in the normal sense to be a frequency of xi on H. So frequency of about 1 in semiclassics is a frequency of about 1 on H in the sort of normal picture. So under this mapping, we obtain a symbol. Xi squared comes from the Laplacian term, then we have some sort of sub-principal part coming from the potential. And in fact, given a symbol, and under some reasonable assumptions about the growth of that symbol, we can define a semi-classical pseudo-differential operator, which is incredibly similar to the normal pseudo-differential operators, only we have this scaling factor. So this is oscillating very, very fast, and we're going to send H to 0.
So will you assume that V is going to infinity here or not?
Showing what?
Will you assume that V grows at large x, for large x, or not?
Compact space.
Well, we're using
Well,
compact
you're a
spaces,
compact
or we're localizing, so
So you're-
we don't make any assumptions about what it's. This is equivalent to being on a compact space, or you can do non-compact, but you're looking at localized properties, because we're going to patch things together.
Okay.
The scaling here, h to the n, is somewhat arbitrary, but the reason we pick that particular one is to obtain L2 boundedness, and that's exactly the right scaling to give us that. So this is our semi-classical pseudo, which is going to be the operator we're working with.
But it's going to be an approximation, what, to some kind of parametrics for this thing, or what?
Yeah, well, this is the operator, and we'll get a parametric solution to solve pxu is equal to 0. Or in particular, we'll allow a little bit of an error as well. So we're going to get our intuition from the links between quantum and classical mechanics. And over on the quantum side, we have a very important part as due to the stationary states, and they satisfy this equation. So this is what we're going to want to solve and get a parametrics for. And we understand that h to the minus 2 is the energy, and we interpret L2 mass probabilistically. So you want to know the probability of a particle being in an area, you measure the L2 mass in that area. Now contrast that with classical mechanics, where we don't talk about probability, we know exactly where a particle is and how fast it's moving. And we have a set of differential equations which tell us where, given an initial condition, a particle is going to end up at time t. So we want to use the fact that heuristically we expect that quantum mechanics should converge into classical mechanics to give us some idea of how to proceed. So when I said we're going to work with localized functions, this is what I meant. We'll assume that for u, there's some kind of semiclassical pseudo that acts pretty much as the identity, and that this semiclassical pseudo is compactly supported about some point x naught xi naught, and we'll patch together a number of different ones of this form. So the idea is to make a little packet which is reasonably well localized in both frequency and space. And we say that we expect for short time the packets will track along the trajectory. So we'd start with a point x naught here, give it a kick xi naught, to get a trajectory in the classical sense, and then we'd start with a localized packet, and we expect that that will track along the trajectory. For some time scale, for a short time scale. In fact, you can reasonably do this up to sort of log time scale, pushing the boundaries of it, but in fact for this problem, just small time. So we're fine on that side. There are some very interesting problems on what happens when you try and push further for longer times. That's the hard part. So we expect that time spent in a region will gain concentration in the region. The more time spent there, the more concentration we'd expect to see. So firstly, we're going to do one major reduction, and that's we're only going to look where the symbol is 0. This is because we can invert it when the symbol is based away from 0. So if you think about going this Fourier method, if p only depended on xi, we could, and it was bounded away from 0, we could invert on the Fourier side, so we can definitely invert on the spatial side. That can be extended to this semiclassical pseudos. So we say, suppose u approximately solves this equation, so we allow a sort of order h error. If p is invertible, then u is small. If u is small, it's not making a big contribution to the concentration, so we can ignore it. This gives us the L2 estimate, and then we can use Sobolev estimates to get us the LP estimates from here. So as long as we're bounded away from 0, we get very good estimates. We're not going to worry about that. We're just going to focus on the place where the symbols are 0. So in this setting, we've got a result by Koch, Tartaru, and Swartzky, which is the analogous result to SOGS spectral cluster result. So they take a semiclassical pseudo-differential operator and an order H quasimode. And they get LP estimates for the order H quasimode, which are the same as the LP estimates SOG got for clusters. Once you go between that H to the minus delta growth is the same as lambda to the delta P growth. The assumptions that they need on the symbol are that it vanishes simply. So we can't have the gradient vanishing at the same time as the symbol, and a curvature condition. So fix x naught, consider those xi for which the symbol is 0. We need that they have some curvature here, and this is often called a dispersion condition.
And if those don't hold,
then the estimate doesn't hold. You can get some other things, but particularly we really want this dispersion. The dispersion estimate is very important for spreading out of waves. So how do they do this? So the first...
Let me try to understand. Does this, just a simple point, does this then give you information about the eigenstates of the original operator or not?
Yes, yeah.
So you get the same, so this is
yeah, well, an eigenstate is a quasimode. So therefore, I mean, it's a perfect quasimode. So anything about quasimode will definitely give you anything about eigenfunctions. Just the same as spectral clusters will give you eigenfunctions, but it's more general information. So starting with the first condition, so this is the gradient condition, we're going to use the implicit function theorem to rewrite P. So we'll factor out some EXI, which is bounded away from 0, and we don't care about it. Then this is the important term. We have some xi1, which we've changed coordinates so that this is nice. Then we get an A, and it doesn't depend on xi1. So this is what we're going to create an evolution operator out of. And from an evolution operator, we're going to get a parametrics. So under quantization, we know that xi1 goes to h dx1, and then we have some kind of quantization for A. So if we allow x1 to be time, then we end up with an evolution operator which has a time derivative here. A doesn't have any derivatives in time, so we're going to be able to solve that in typical parametric methods. So we let x1 be time, and we're going to try and solve this evolution equation. So just to show you what this would look like for the Laplacian, so consider sort of localized quasimodes for the Laplacian on Rn. When the symbol is 0, that means xi is on the sphere of radius 1. So these are the xi for which the symbol is 0. So you pick some xi naught and put a cutoff function around it. Consider a local number of frequencies that are close to xi naught. And this produces a packet where the principal oscillation is in the same direction as xi naught, and then we have some sub-principal oscillation. Notice that you have the curvature, and this gives you the dispersion. So for the Laplacian, the principal oscillation becomes the time direction, and then you have your other directions in which we're trying to use dispersive estimates to determine concentrations. So that's the case for the Laplacian. And in general, what we want to estimate is this mixed space-time norm. So because one of our spatial things has now become time, we have LP in time and LP in space. And for those people used to dealing with evolution equations, this immediately suggests using a Strickhart's estimate, because
Your time is the x1 now, right?
time is x1. So we're thinking of that as being one of our spatial.
Yeah.
So we want to use Strickhart's estimates because they give mixed space-time norms. And the form we're going to use is the Kiel-Tau abstract Strickhart's estimates. And I've put in the assumptions here and added in a semiclassical parameter. So Kiel and Tau has truncation of order 1 or no truncation at all, but for this you want to truncate at a semiclassical level. Sorry? No, we don't need endpoints for this.
Somehow the highlight of the estimate is that it gives an
Yeah, yeah. The highlight of Kiel and Tau is the endpoint estimate, but for what we want to do, it's just that they do it in a very nice framework for the estimates that I would like. We don't have to worry so much about the endpoints for this particular use. So we have an L1 to L infinity dispersion estimate, and we have that U of t as a unitary operator. Under those conditions, we have mixed LpLr space-time estimates in terms of U in L2, provided P and R satisfy this equation. And we're going to be trying to set P is equal to R, find sigma, and then solve for P.
So does this follow directly from the Kiel-Tau, or do you have to do something else?
Putting in the semiclassical, it's just a matter of tracking the algebra for Kiel-Tau. It's conceptually the same, it's just keep track of your terms. So going to do this, you would write out x as tx bar. You've got a solution to an evolution equation, which for semiclassical analysis we can get a parametrics for, and this is the form that we want to use. So a couple of things to note. We've got h to the n minus 1 here. That's because we've lost one dimension, has become time. Phase function phi is given by this equation, the I-kernel equation, which allows us to take information about the flow into information about the operator. And this equation is key to obtaining any of our estimates. And because we've got this I on h term, so it's oscillating very fast, we want to use those oscillations to get some cancellation, and so we're going to be using stationary phase methods to get the L1 to L infinity. Later, when I'm talking about hypersurface estimates, I'll go through this a bit more closely, but this is the estimate that Koch, Tartaru, and Zworsky obtained. You've got a growth in h of n minus 1 on 2 and the similar decay in t minus s. And to prove these, you need the dispersion curvature assumption. Now, substituting into Strickhart's, setting p is equal to r, solve for p, we obtain p is equal to 2n plus 1 on n minus 1. So that's how we find our critical point. You can mark this in and then just interpolate to get all the other estimates. So now we have this for semiclassical quasimodes. So what about submanifolds? And that's what I've been working on. What can you say about extending Berkshire-Arden-Svetkoff's submanifold result into this framework? And what you get is you start with PXHD, the same semiclassical pseudo. You have your same order H quasimode, and you end up with the same kind of growth. So this delta NKP is the same one as Berkshire-Arden-Svetkoff obtained. The assumptions that I need on the symbol. So I still need the same gradient one, and I need a curvature assumption. However, my curvature assumption is actually quite a bit stronger than Koch-Tartaru and Swartzky's. They only assumed that this had non-zero Gauss curvature. But I'm going to be wanting to take cross-sections through it, and I need every cross-section to have non-zero curvature. So I need this positive definite second fundamental form. It's a little bit stronger. So we're just going to look at hypersurfaces because that's where all of the interesting results are. So we can still assume localization properties for hypersurfaces, and so we can reduce to where the symbol is equal to 0. We can still introduce the evolution equation, exactly the same as Koch-Tartaru and Swartzky. But now direction matters. For them, they could change their coordinates in any direction, didn't matter. What we want to know is once we find that principal direction, how does it relate to the hypersurface? Is it something like this, where the principal direction has some normal component to the hypersurface? So a particle starting here would flow directly past the hypersurface? Or is it something more like this, where the direction lies along the hypersurface? And we need to break into cases and treat them separately. So the first and easiest case is if you take xi that is dual to nu, take the derivative in that direction. If that's non-zero, so this is the case where if you have a hypersurface, start a point here, this is equivalent to saying the velocity in the normal direction is non-zero. So a trajectory would just run straight through the hypersurface. So you would expect that a packet tracking on that trajectory would also just pass through quickly, not leave much concentration. And that's exactly what you find. So you use the fact that h is now a time slice, and you've got a unitary operator. Therefore, u restricted to h is bounded order 1. So that's just saying there's no L2 concentration at all. And this is the best result we could possibly hope for. So we can ignore this case, put it to the side, and just look at the place where d xi nu p is equal to 0. And that will give us all of our estimates. So again, we're going to split x up into t and x bar. And x bar now has a splitting, so x dash and nu. T and x dash are the coordinates on the hypersurface. This is one-dimensional, n minus two-dimensional, and nu is the normal. It's one-dimensional. So we have these free coordinates. Then we're going to try and solve the evolution equation again. We can do that, write our parametrics up for u of t, and we define w of t to be a composition with the restriction operator. So we propagate our initial condition, and then restrict it to the hypersurface. Now we'd like to get mixed space-time norms for w of t, and want to use Strickhart's estimates again. However, in the assumptions that we usually put about Strickhart's estimates, we're dealing with unitary operators. W of t is not unitary, not even close to being unitary. So we can't directly apply the Strickhart's numerology. However, when you look at the proof of Kiel and tau for the non-endpoint cases, it doesn't really matter that you assume unitarity. What matters is that you have an L2 bound to interpolate from. So instead of assuming unitarity, we're going to assume an L2 bound to interpolate from. And we'll assume one of a similar form from the L1 to L infinity bound. So now these two assumptions come out in a symmetrical format. They both have some t minus s decay. And under these assumptions, then you get the same sort of mixed space-time estimate under a slightly different governing equation. So notice if you put sigma 2 is equal to 0 here, you recover the standard governing equation for a normal Strickhart's estimate. So this is the form we're going to be working with. And I'd just like to briefly show a sketch of how you would go about proving it, because understanding that helps you understand why you get these two regimes. So the proof goes first by putting it into a bilinear form. So we're going to take an inner product here of W star TF, W star SG, then we integrate in S and T. And if we can find that it has the appropriate H growth times the appropriate norms in F and G, we will have our Strickhart's estimate. So in fact, what we're going to do is just put an absolute value on the inner products and get estimates from that, and then do the T minus S integration. So here are the assumptions we've made, the energy and the dispersion assumption. Energy if I is equal to 2, dispersion if I is equal to infinity. Now when we have these, we can interpolate between them for every value of P between 2 and infinity and obtain an estimate of a similar form. Now we need to do T minus S integration, and we're going to use Hardy-Littlewood-Sobolev to get the correct fractional integration. So just showing it as a diagrammatic form, we start with our spatial estimates in L2, giving a gamma of sigma 2, and L infinity giving a gamma of sigma infinity. Interpolation matches up for every value of P, a value of gamma. Then Hardy-Littlewood-Sobolev tells us for each value of gamma, we have one value of R, which is just right for the fractional integration. When we combine those two bits of information, we get the governing equation. So now we have the Strickhart's estimates that we're going to use. We already have the dispersion, L1 to L infinity norm. It's the same as Kosh-Tartaru and Zwortsky. However, we need a bit more information. The way they obtained this L1 to L infinity norm was just to take absolute values of kernels. But when we want to take an L2 to L2 norm, we want to know about oscillation. So we're going to need a better description of the kernel than they had. So just in trying to avoid ending up with long, complicated calculations, I'm just going to do this for a model case here. So the model case is xi t minus xi bar squared, which when I write it out to separate between the dashed variables and the new variable is xi t minus xi dash squared minus xi nu squared. And in this case, you can write a very nice expression for Wt W star S. You have the same usual scaling out the front, an oscillatory term, and the propagation is given by T minus S xi bar squared. This is the simplest case, but actually this is pretty much what you get in the general case with some error terms hanging around that don't really hurt what we're going to do. So firstly, we're going to integrate in xi bar, and we're going to use stationary phase. So we need to determine where the critical points are. And just from a direct calculation, there where x dash minus y dash is equal to 2t minus s xi dash, and where xi nu is equal to 0. And the non-degenerate critical points too, so long as t minus s is not 0. Now, the other thing this equation gives us that if x minus y is too large, there are no critical points, and then we'll be able to just integrate by parts several times and get some good estimates. So all of this, putting it together, what do we get for the kernel? Well, we have decay. That comes from the standard stationary phase decay. Xi bar is an n minus 1 dimensional object, so non-degenerate critical points give us n minus 1 on 2 decay. We evaluate the phase function at the critical point to give us our oscillations. Then B is a symbol which is smooth, differentiable, we can do anything we like to it, and it's 0 when x dash minus y dash is too large. So that combines the information we got from our previous critical point estimate. So this is just a description of what the kernel would look like as you increase t minus s. For t minus s sort of size h or smaller, you've only got space for one oscillation. So you get something that's very high L infinity norm, but you don't see any oscillation yet. As you increase t minus s out, you start to get some oscillation. So you see one oscillation there, as t minus s gets bigger, you get more and more oscillation before the cutoff function makes the kernel 0. So we've got the L1 to L infinity estimates. And what we need to do for the L2 to L2 estimates is use the oscillations. If over here, where we've got a lot of oscillation, you consider a point that's sort of oscillating in this direction, one that's oscillating over in this direction, they don't overlap very much. We've got orthogonality in L2. So we want to use that orthogonality to obtain some good estimates.
Again, I'm confused because when t minus s is, if you look at this kernel, it's when t minus s is small that you get the oscillations.
Well,
You're looking at the exponential factor there.
but you've got a cutoff factor as well.
Ah, okay.
And that just takes,
Okay.
so the kernel is 0. It's only supported on a ball of size t minus s. So if you didn't have the cutoff function, yeah, you'd have plenty of oscillation there, but the cutoff function means you don't get a chance.
Somehow these calculations are quite reminiscent of some parts in Berg-Svedkov and Gerard's paper.
Yes. Yes. You can go through and directly sort of make a link between each particular calculation. And they all follow the same thing. You've got your kernel, your L1 to L infinity estimates, and you do some kind of almost orthogonality result.
But that would this would fit in the first, the general frame where you have something. So the restriction is that there are no assumptions on curvature of the hypersurface.
Not yet. You can get better things if you assume something about the curvature of the And I'll talk about that actually in a minute. So what we're going to use the fact that L2 is a Hilbert space, and that allows us to take a nice square of the norm. It's a very, very common and well-used trick throughout this area. So we're going to write it in terms of this k tilde, where k tilde, you combine the two kernels and you get to integrate out, which sort of smooths out your estimate. And you get a phase. So what's a phase function? Well, you get x dash minus y dash coming from the first kernel and x dash minus z dash coming from the second kernel. So if you take a gradient in x for these, you find that there's no critical point unless y dash is equal to z dash. So this is great. This is the best place we could be in terms of using oscillation. We can just integrate by parts. And every integration by parts is going to pick up a h factor, because we're oscillating at 1 on h, and a t minus s factor from here. But because of our symbol, which has small support, we're going to lose that t minus s. We pick up 1 on t minus s from each differentiation of the symbol. So putting that all together, we say that the principal contribution comes when there is no oscillation. When is there no oscillation? Well, that's when z dash is very close to y dash, and very close is of order h. Further, x can only be out to t minus s from y. So our concentration comes from this little area, and both z dash and x dash are n minus 1 dimensional. So the contribution is h to the n minus 1, t minus s to the n minus 1, n minus 2, sorry. Putting this together, so we already had some L infinity estimates for the kernel. Then we put together this contribution from a very small region in space. This gives us the square of the L2 estimate, so then we need to take square root, and we've obtained the form that we wanted for the L2 to L2 estimate. We have a growth of h to the minus a half put against a t minus s decay of h to the minus a half. So putting this together, we already had L1 to L infinity dispersion estimates of this form. So we have sigma infinity is n minus 1 on 2 to put into our Strickhart's estimates. From our description of the kernel, we obtain estimates for L2 to L2, so sigma 2 is a half. Now we can stick this into our Strickhart's governing equation, set p is equal to r and solve. And we obtain a critical point at 2n on n minus 1. So now we've got that critical point gets to go in, and we can link it to the L infinity estimate that we already had. For L2, we just estimate directly from our L2 to L2 energy estimate, and that gives us 1/4 for the growth. Then just interpolate to get everything between. So now that gives us the complete set for our hypersurface. For a submanifold, you find that there's no point from the Strickhart's estimate. You get everything just by directly estimating the L2 and interpolating with the L infinity. And that's because we don't have this regime change, and the regime change is driven by what's the major term. Is it the truncation in H, or is it the T minus S? And the fractional integration part of Hardy-Littlewood-Sobolov that we did in the Strickhart's proof of the Strickhart's estimate tell us that at P is equal to 2n on n minus 1, the major part changes over. Before that, the truncation is what matters. After that, it's this T minus S decay that matters, and at that point, they each have a sort of equal contribution. So that's why we end up with a regime change. All right, so I've said that they're sharp, and they can be found sharp examples for tubes. Now, the sharp examples correspond to a tube which is around a geodesic or flow line that is trapped on the hypersurface. So this is a point about curvature. We need this to remain always on the hypersurface, and then anything that is tracking along this curve will always have to remain close to the hypersurface. It won't be able to vary off it very much. That's how we get the tubular concentrations. But this is an extreme case. Our assumption is only that the velocity is 0 for this flow line. And it's an extreme case to then assume that if the normal component of the velocity is 0, then it must always lie along the hypersurface. You could in fact have the normal component of the velocity being 0, but for instance, the acceleration being non-zero. And so this is the curvature case. So in this case, we say, okay, what if we start a point here? It has its velocity at its starting point is 0 in the normal direction, but its acceleration is not. Well, a particle tracking, packet tracking along here, it will spend more time near the hypersurface than one that just struck through, which is the best case, but less time than the tubular sharp case. So we would expect to have a smaller concentration. And in fact, that's what you do find out. So you obtain this delta tilde for the growth, and for L is equal to infinity down to the kink point, it's the same as before. If you think about it, we've got sharp concentrations, or the point concentration, you can just put a point concentration anywhere. So geometry is not going to help you very much here. However, for the tubular region, you do obtain a better estimate, and you get h to the minus 1/6 growth rather than h to the minus 1/4 growth for L is equal to...
Geometric setting, what's the assumption here?
Sorry?
If you're on the sphere, the first curve was sharp.
Yep.
So what's the geometric assumption?
The geometric assumption of... To go to the red curve. In general, it's this assumption says that the flow always glances against.
Right.
So
This is like restriction to a thing with curves.
yes, so if it's a Laplacian, the assumption then becomes that the hypersurface is curved.
Maybe, okay.
And a curved hypersurface will have flow glancing for a Laplacian.
Right, so I still consider that to be a different sharp X. Okay, I understand. So in their case, they have that curve.
Yeah, so for them, when they did the Laplacian, their assumption is that the
curve with strictly positive
curvature, strictly positive curvature, bounded away from 0.
And then the exponent changes.
Then the exponent changes. If you want to do it in the semi-classical, you state it in terms of this acceleration condition. So Berkshire, Arden, Svetkov did that for n is equal to 2, and then Hu extended it for higher dimensions under the same conditions. Then for semi-classical quasimodes, this is a result by Hassel and myself, where we state the condition in terms of acceleration. So we want to obtain this better estimate. And so far, we really haven't used the T minus S integration in terms of oscillation. So when we did our Strickhart's estimates, we just put absolute values on the side of the inner product and then did the integration. We didn't leave any room for using oscillations here. And the reason is that for the tubular concentration, there is no useful oscillations. So we may as well not consider them. However, in the curved case, there are useful oscillations in T minus S. And having this curve glancing against the hypersurface creates a fold in the canonical relation. So we use the Melrose-Taylor Fourier integral operators with folds description. And that's for regularity of 1/6, and regularity as a general result always corresponds to growth results in terms of eigenfunctions. So we're able to apply a form of Melrose-Taylor to be able to get this h to the minus 1/6. Okay, so this is just a bit of a summary of where we have ended up. We have estimates for submanifolds in terms of n, k, and p. For dimension n minus 1, so in the hypersurface case, we have a 2 regime in terms of sharpness. We have the high p estimates, which are made sharp by points. For low p, we have a general estimate, which is made sharp by tubes. If we can assume a sort of curvature glancing flow assumption, we can get better results for p is equal to 2 and all intermediate ones. For lower dimensional submanifolds, we don't have the 2 regimes. Everything is made sharp by a point. And so in that case, we can't do any better with any geometric assumptions because we can always just put the point down wherever we like.
So what are those 2 lines again? You just
These
said,
ones?
yeah. So the
Okay.
red one is
The red one is the better estimate when you make the curvature assumption. And so that's made by getting the L2 estimate using the Melrose-Taylor and then interpolating. And then this is the general estimate that applies no matter what. Okay. So we've got no better estimates for these hypersurfaces, so these submanifolds, sorry. These are all sharp, so even these ones are sharp, and also you can pull out spherical harmonics and show that they're sharp for eigenfunctions as well.
Just wanted to, well, I mean, if you look at the 1/4,
Yep.
so let's say that you take n equals 2.
Yep.
So then you would do a restriction to a piece of a curve.
Yes.
Right? But basically, to get the 1/4, this bound really saturated, that you would need that piece to be contained in a closed geodesic.
Yes,
This is correct.
that's correct.
This is a part of the Tataro story.
Yes, that's part of the
And
Tataro
that
story.
is also for your.
Yes, that's also the same, and for the hypersurfaces and in the semiclassical framework, you have to have sort of an embedded flow line, which is a geodesic for the Laplacian case in the hypersurface, and so that to be able to get this sharp estimate. So you can get sharp estimates for order H quasimodes. To get better estimates, you would have to take better quasimodes. So start increasing the power, for example, on H. But that then gets to be a very difficult problem because you have to start running time for a very long period. And
Depends what your underlying dynamics are. It's integrable.
you could probably, yeah, if you're in a very special case where you know.
Or if you have a flat torus, these guys know.
Yeah, but the flat torus where you have a nice description of the eigenfunctions it's probably better to do it via your description of the eigenfunctions than doing it this way. But in general, if you are going to do something where you need some kind of geometric assumption, because the spherical harmonics show us that you can't do better in general. But this is equivalent to sort of shrinking spectral windows, because a spectral window of size 1 is an order H quasimode. As you shrink a spectral window, it becomes a better order quasimode. And that's the link between the two. So to be able to get better estimates, you'd have to take better quasimodes, make some sort of geometrical assumptions, and deal with the technical problems as they arrive. So I think I'll leave that here. And is there other questions?
Not right now.
Just a point. What you get for quasimodes is true for true modes, but sometimes, like for a torus, for true modes, you get things which are much better than.
Yes, yeah. Yeah, because
So
you can.
the setting in which your generalization seems to me that is if you just have any classical mechanics which is not coming from geometry, then you this is the setting in which you work, right?
Yeah.
You have a
You just have some.
Hamiltonian flow, you quantize it, and then
Yeah.
you get these bounds.
Yeah, you get these bands. Yeah. So any one you like, so long as it obeys the assumptions we've set on the symbol, that's fine. And of course, the Laplacian is always the model case. And
But if I remember what you told us earlier, you also had some results in which your dynamics was, more specific, maybe chaotic,